Okay, we're given a distance curve, and we have it's in seconds and meters. So on this distance curve, from this distance curve, we're asked to graph the velocity of it. Well, don't forget that the velocity is the slope of the distance curve, okay? And if we're going to draw that velocity, then we need to be thinking about each of these segments. Okay, so we have one segment here, a second one, a third, a fourth, and a fifth. So with those, while I don't have actual values, I can make estimates about what the velocity of them is. And for number one, this part of the graph is steeper in a positive direction than any other part of the graph. So since it is steeper, it has a higher velocity, and down here I am graphing velocity. So if it has a highest velocity here, then I'm going to draw, and it has a constant velocity. I don't know what it is again, I don't know the value, but it has a particular value between, I'll say that's A, between 0 and A, it has a constant velocity, okay? For section 2, it has a constant velocity as well, okay? But how steep it is less than between 0 and A. So again, while I don't know what the value is, I know it's a constant velocity, I know it's positive, so I have to be above the x-axis, and I know that it's less than what my first section was. On my third section, right here, that is a horizontal line. At a horizontal line, the velocity is 0. The slope of a horizontal line is 0. So I'm going to mark that off on the x-axis. At the fourth position, okay, now what I know is it is a negative slope, so I'm going to be below the x-axis, and it looks like it is pretty close to the same magnitude as position number 2, even though they're in different, even though one is a positive slope, the other one is a negative slope, the value of it looks about the same. So if I kind of think of this distance away from the x-axis, and I try to put that same amount down here, that might be their fourth one. Obviously, we're not going to be exact because we don't have any specific numbers. And then the last one, number 5, well, it's a steeper negative slope, so I'm going to be farther away from the x-axis than part 4, section 4, but again, it looks kind of like the same distance, the same kind of slope as section 1 or thereabouts, so perhaps the distance in a positive and negative sense should be pretty much equal. So in this problem, a little bit further, we have it, because those are all line segments in here, okay, and their values are very distinct because we have corners where they connect, very different. We end up with the series of jump discontinuities in here. On the next problem down, my graph is nice and smooth. There's no corners, there's no cusps. It's a very smooth, looks like a polynomial function, and we're not going to end up with any jump discontinuities in this problem or any discontinuities at all. So when I look at these kind of problems with a polynomial or something that looks like a polynomial here, what I like to do is I like to determine where my velocity is 0. Because when my velocity is 0, that's going to be shown by the velocity graph crossing the x-axis. So that happens at my max and min of the function. My velocity equals 0 there. And so I show that again on the x-axis. Now for the next part I like to think about is, where's my function positive? Well, where does it have a positive slope? It has a positive slope in this region here, okay? Some of it is steeper than others, but it's all positive. So since it has a positive slope, that means my velocity curve has to be above the x-axis in here, okay? Where instead, on the part after 12, this section in here, my function's going to have, it has a negative slope, so I have to draw my graph somewhere below the x-axis. A negative slope has to be below the x-axis. Okay, so how do I connect that information? Well, in order to put it all together, I have to start at 0, okay? And the slope of this function is getting steeper and steeper as I go to a certain point right about here, okay? The slope is getting bigger and bigger, and that's shown by different values here, higher velocity values. And then, while my slope is still positive in this region, it is less steep. It's getting closer and closer to 0, and it's at 0 when it's at 12. So it's a positive slope. Positive slope's above the x-axis. Still positive slope, but it has to go through 0 at 12. It's not as positive. It's not as high. As positive doesn't make sense. Okay. Then after 12, this part of the graph again has a negative slope, and that slope keeps getting higher and higher in a negative direction. So it continues to go down in this direction. A note of caution for those of you who take physics. In physics, you're only ever working with a parabola function. You're throwing balls up in the air and that sort of thing, and they're coming back down. And some of you know that graph will end up, the graph of the position of a ball is a parabola. The velocity of it is a straight line. Now in our case, we are working with functions that are a higher degree. So a parabola has a degree of 2. In this problem right here, this function has a higher degree. I don't know what it is, but it definitely is not a parabola. So if the function is a parabola, yes, I agree that we will have a linear velocity graph. But that's the only time your function's going to be linear. As we do more of these kind of problems, you will see that what my statements there hopefully will become more and more clear.